Welcome to Astronomy on Tap. I'm not an astronomer. I'm actually what is called a theoretical physicist. My training was actually in particle physics. So the physics of very, very small things, subatomic particles. And in fact, beyond that, what could be actually, our deepest understanding of physics at really the very tiniest scales. So then, how does somebody who thinks about that ends up working on something to do with an astronomy-related subject, which is cosmology, which is really the structure of the universe at the biggest scales. And crudely, actually quite accurately, the answer boils down to the fact that the universe is expanding. So if we run that film backwards, it kind of works like a microscope, right? So like if the universe began in a very, very tiny, dense thing, then maybe things that were really, really, very, very subatomic could maybe have some remnant evidence left over, blown up. And as I'll get to later on in the talk, I think the question of what is the universe at the largest scales comes down to understanding this physics. And one of the questions that immediately comes up is, well, what is the universe? What is it? Like, is it something that had a beginning? And does the question even make sense to ascribe that notion to it? Because things like space and time, these are all very intuitive concepts that we have at our scale, but it's unclear whether the universe actually cares about our notions of it. So I think an interesting thing to do is, am I doing the right thing now? Yeah. Is to rephrase or just step back a little bit and sort of ponder the question, does it even have to have a beginning? Why should time even have a beginning? And so this question actually was preempted by many, many ancient traditions. In fact, the vast majority of them. Hinduism, Buddhism, various pagan traditions, Egyptian cosmology, put time on a circle, which really very much avoids the question. And of course, it's a natural thing to do because it very much syncs up with the cycles that we see around us in nature. And so I think this is a key thing to understand, which is that depending how you frame things, questions may or may not even arise. So this may seem like a pretty abstract thing, right? What does time have to do with? Like, what impact does it have on my life? I think it's one of the more startling things. So I may come off as somebody who is quite westernized to you, but I'm not a Westerner. I left Asia when I was 18 years old. So my thought processes are actually very different in ways that I see things and I understand things that and you would have the same viewpoints as if you went to a different culture. I think one of the most startling things about this question is how much it actually has permeated every aspect of our lives. One of the things that people, I think, content themselves as a fiction within Western societies is that we live in a secular society. It is completely untrue. Christianity has found ways in which to get into almost every structure that governs our lives. And this is one of my favorite philosophers. He's an intellectual historian. His name is John Gray. And intellectual historians are, if you like, anthropologists of ideas. And one of the things he points out is there's a millenarium, i.e. there's a beginning, and then there's a rapture. There's an ultimate end state, which everything has to head towards, underpins all of our social structures that we, at the bottom, have some sort of utopian thinking underlying it. And this comes up again and again. So, free market capitalism, we're all headed to this amazing place where liberal democracy rules everywhere, and we all live happily ever after. Or communism, if you have a more egalitarian take, or you name it. These are some really incredible books I strongly encourage you to read. But one of the things that John Gray really likes to point out, and this is actually where I picked this out from, the basis of the talk, is that Christianity is a revolutionary idea. Because what it does is it put time on the line. And when you do that, that immediately forces you to ask questions like, how did it begin? And if it has a beginning, does it have an end? Right? So these are questions that would not occur to somebody living in a world where time is a circle. So now this, by the way, led to quite a lot of sustained, if flawed, inquiries into the origins of time. There are actually linguistic proofs by Islamic scholars and Origen of Alexandria that deduced that there had to be a God. Because if something happened before it, and then blah, blah, blah. You get the picture. They're all sort of arguments based on the tools of inquiry that were available to these people, which is linguistic. Now I should stress, and I should contrast this to traditions from my part of the world, where it was very, very much understood and warned that do not fall into traps of linguistic reasoning. They will lead you into cognitive traps, rhetorical traps. You will misunderstand the nature of reality that way. So Dharmic traditions had a very different take on this, but this is nevertheless how this question began. So it comes then, so just to stress how revolutionary it is to decide that time is a line. It comes as a bit too on the nose a detail in the annals of the history of science. That the first person to have ever written down a solution to Einstein's equations, Einstein of course came up with the theory of gravity and how matter interacts with it. The first mathematical derivation of an origin to the universe was done by a Catholic priest named Georges Lemaitre. In actual fact, he's a professor of physics at Université Catholique de Louvain, and you have to be an ordained priest in order to become a professor at Louvain back in the day. But that's what he did. And so he actually stared at Einstein's equations. They were so complicated, they're really, really difficult to solve. So he asked the question, well, what is a solution where if I just assume that there's no center and everything looks the same in this direction, every direction, no matter what angle, you come up with this solution that has as a obvious consequence that it all sort of expands from this really dense primal state that he called the primeval atom. And that is the beginning of what ended up being Big Bang cosmology. So we all have heard of it and we know about it. And the idea is that the universe began in some sort of a dense fireball, and various things happen. I'll try to give it a slightly more. I'll show them a few more pictures of what that might look like in a second. But this is the sort of the basic picture, and it's notable because it actually raises as many questions as it answers, because the first thing, and by the way, this is actually the reason I think I became a physicist. I was one of those really annoying children that would ask a question, my dad would give me an answer, sometimes make it up just to mess with me, and then I'd get really angry, and then I'd go find out, and then find another explanation, and then I'd keep asking, well, why that, right? And then I'd get another explanation, well, why that? And then at the end of the day, you inevitably end up with in these very reductionist, basic explanations, and you could have asked the question, well, somebody tells you that the Big Bang is the solution, but why the Big Bang? What happened before? I'll get to that later. But so it's really an incomplete picture by its own construction. And one of the weirdest things about it is that it came with sort of little fluctuations, if you like. The Big Bang began with little fluctuations. That was the beginning of gravity beginning to collapse whatever was produced in the Big Bang into little clumps. And if you take that film forwards and just evolve it, this is a simulation done by someone in Germany, Dr. Matthias Höft. What you end up noticing is that these tiny little ripples, whose origins that were just sort of, you just have to assume that they're there in the Big Bang cosmology, ends up forming the scaffolding around which clusters of galaxies eventually formed. And this is what, it's a bit of an outdated picture, I apologize. I know people from Euclid will have much nicer pictures soon. But if we stare out, oh, by the way, what is this wedge? This wedge is our galaxy. We can't really see through it. It's a bit annoying. So if we look up and down, this is what the universe looks like. These are actually these dots are clusters of galaxies. So I mean, it's weird. We can't even. I mean, a galaxy wouldn't even be a pixel on this, but nevertheless, there were these little ripples, who we don't know where they came from, or I'm about to tell you what our idea is. And they formed everything that we see around us. So everything was just the net effect of cooling this primordial soup into all the stuff that we see around us: stars, galaxies, human beings. Where did these seed fluctuations come from? That's really one of the questions that was left as a mystery for the Big Bang. So the Big Bang itself is incomplete. And this is actually a picture of what those seed fluctuations are. It's the so-called cosmic microwave background. Maybe you've seen a picture of it, maybe you haven't. But I can easily explain this to you if you've ever driven in the morning and you've been driving through mist and you can barely see anything, and then suddenly the mist clears, and now you can see everything, right? So that moment happened actually in the early universe. There was just so much going on that light had a really hard time just sort of traveling in a straight line, like in mist, it's all scattered. But then there was a moment when electrons and protons found each other and formed neutral hydrogen, and then light could just flash around. And that flash we see. It happened when the universe was about 374 to 378,000 years old, and this is an actual picture of that flash. And we're starting to see the ripples that ended up forming these clumps that form the galaxies that we see. So where did this come from? So now I could give an entire like a semester-long course on this, but what is the origins of these ripples and where do they come from? It's going to lead us to our current model of cosmology, and then I'm going to tell you why I don't believe in it. I just need to make a quick detour into something that I hope is intuitive, but it has other manifestations that may not be so intuitive. But you've probably never seen any body surface of water ever still completely. Right? It's always little fluctuations. Why is that? Because things happen, things are dropping in, things are moving around. Things are always being disturbed, so it's fluctuating. So now imagine I had perfect laboratory conditions and I got rid of all the things that could cause it to ripple. I'm looking at a pond, I'm putting it under some springs, I'm shielding it from all the vibrations that could be around it, and I'm trying to make it as still as possible. I turn down the temperature to zero, as close to zero as possible, just to make it as still as possible. And it's still going to have little fluctuations. And what those fluctuations are what we call quantum fluctuations. One way to think about them is, I think, if you imagine what a thermal fluctuation is, so you boil a pot of water, things jiggle around because they have a high temperature. Even if I turn that temperature down to zero, there would still be some irreducible jiggling, and that is because of a property of quantum mechanics known as the Heisenberg uncertainty principle. You don't need to know what it is, but for those of you who want to understand it, it's saying that you cannot know where something is and how fast it is going to arbitrary precision, meaning that the statement that something is at rest forever is a contradiction. Okay. Means that that's saying that you know both to arbitrary accuracy. So if you allow for some uncertainty, it just means that things are always just jiggling around. And this is an irreducible property of reality. So if you like, take this as someone's just telling you this is how it is. This is how we've observed the universe to be. So what is the Big Bang? This is what we think it is. That there was this phase of evolution called inflation. I'll tell you what it is in a second. Where itself it had some quantum fluctuations that when that thing ended, you're seeing the effects of those fluctuations in what was left over. So inflation is a phase of the early universe where the expansion of the universe just really accelerated very fast. There was some thing that did it. We call it a field. Okay, so in physics, physicists and particle physicists, we like to use this concept of fields. There are things that are sort of making forces and making particles appear in different places and interact in certain ways. This thing made the universe expand really fast, so it made it the same everywhere. And then when it was done doing its job, it dumped all of its energy, and it thermalized, and it gave us the Big Bang. But we know that nothing can have imagine this thing being a field, so it has like a if you like this, imagine its surface, and it's got these little jiggles, and that's what these seed perturbations were. So this is in a very crude, perhaps not very satisfactory way, an explanation of our current model of cosmology. This is called the standard model of cosmology. This is the underlying picture that the universe began. The universe began as the end stage of this phase called inflation, which set up the Big Bang, and the quantum fluctuations in that process gave us what we see. And so the picture is from those fluctuations, then those fluctuations started collapsing, and of course there's a little bit of time before things weren't quite finding each other, but eventually things got to such a density that there was enough clumps of hydrogen that they started to form these controlled gigantic hydrogen bombs called stars. And this is this period here, where suddenly stars start to appear and the stars start to find each other and they form galaxies, and then we are over here, and now we're looking back and trying to figure out what happened. So, but you could have asked, what happened before inflation? Okay. So now this is where my life as a theoretical physicist began. I was actually working on this question. And if you know this, and if you have an idea, how could you know any better? Okay. So that's the job of a theoretical cosmologist, and we work at different parts of that question. And the answer is we don't know. Okay, yet. But I would like to posit that there are some things that we may never know, for very obvious reasons. But this is just one idea. It is, in fact, if you take this idea of inflation to its logical conclusion, a lot of people actually have come to the realization that, in fact, what we are is just a bubble in a thing called a multiverse, where there are many other universes that this field just sort of populated around. This is an unavoidable idea if you believe in that other thing. I could, if you want to understand more why, you could ask me later. That is consistent with what we see. The other thing is, it could also have been a series of bangs. This is another idea that people had entertained. The question is, which is true? And so in order to actually figure that out, you have to make predictions. You have to say, if this is what your model of the universe is, then I could see this. And that is the kind of job that occupies us. There is a really striking idea coming from this theory called string theory, which we don't really understand, but we nevertheless try our best, that actually, quite naturally, explains all the mysteries we had that we couldn't quite piece together in our understanding. But the problem is it always comes with all these extra ingredients we don't know what to do with, and one of them is extra dimensions. And so some people decided to just embrace it and say, quite possibly, maybe the universe, like books in a page, pages in a book, we are just one three-dimensional slice in a higher dimensional membrane, a higher dimensional multiverse, and we don't actually see the words on the other pages. We're sort of stuck because we're described by these things called open strings that are just sort of stuck on these pages, and only gravity can go across these different membranes. The idea is that maybe the Big Bang is two of these membranes coming together and periodically clapping every 13 billion years. All of these ideas are in play, okay? But nowhere have I yet to actually address the question, did time have a beginning? And does the question even make sense? And the reason this is a tough question is because actually cosmologists, we're actually more like archaeologists than anything else. Okay? What does an archaeologist do? They look at some evidence, usually obscured by dust and different things piled up on top of it, and try to infer what happened from what they see. And that is exactly what we're doing as cosmologists. We actually just have some thing we're trying to look at, trying to infer. We have very limited data. And in fact, we are obscured by our own galaxy, which has a lot of dust in it. Okay, so it's quite a literal analogy. And we're trying to look past this, and of course our information is going to be as limited as what we can hope to observe. And so it is an environmental science, actually. It's an inference problem, and it's very, very difficult to actually to ask all the questions we would like to. I think there's actually a really profound philosophical thing that I think only cosmology comes up against. Imagine you have a theory. All of our theories in physics give you probabilistic, it's just an irreducible part of quantum mechanics, probabilistic predictions for an ensemble of observations. So if I could repeat the universe 1 billion times, I can confirm my theory or not. But we only have one universe to look at. right? So this is a very profound epistemic limit to how well we can actually answer the questions we would like to. But this is actually where I actually get some satisfaction, which is that ultimately this question actually starts to lose meaning. If you look at a table, right, or your chair in front of you, and you think it looks pretty solid, but you know if you zoom in enough, it's not solid. It's actually made up of little grains and maybe bits of like fibers, and if you keep zooming, there's like molecules and atoms and so on and so forth. And if you keep zooming, it's basically empty space, right? It's, protons and neutrons and electrons rolling around it. Is the same true of space-time? Turns out that every approach you have, I mean, this is completely not uncontroversial statement I'm about to make here. Everybody agrees that this is going to happen. If you zoom in enough on space-time itself, it eventually stops looking like a continuum. It has to. Because imagine this fluctuations that I was telling you about, these quantum fluctuations. Eventually, if you zoom in enough, they become so big, they become so violent, that they can actually form little black holes right then and there. So it evaporates, and comes back together. Space-time at the very shortest scale is fractal. And we don't even know how to write down a theory that can describe anything on this. We're still very likely, concepts such as space and time are actually emergent. They're not a thing that we put in and do things on top of. They're a product of doing things. And our understanding of this is very primitive so far. So the question of does time have a beginning is about as meaningful as where's the edge of the earth. Right? It's a bias you have from thinking linear. If time was a sphere, that question wouldn't mean anything. And I argue that even the notion of time and space itself breaks down. So maybe there's an actually hard epistemic limit that says that we will never understand the origin of the universe if we're made up of stuff like that. So, and that's okay by me. One of the things I really like about being a physicist is it's the only field of human inquiry I have ever come across that actually says, that is a meaningless question. It's the only field of human inquiry that negates itself, that says you cannot ask this question, it is a meaningless question, move on. And that's where that might sound unsatisfactory to you, but I happen to think that asking the true order in the universe is we'll never know. It's just not a meaningful question. So long as we're made up of the material things that we're made up of, with the brains that we're made up of. So that's all I wanted to share with you. It's a question that you can always ask what happened before, and if you keep going, without doing too much thinking, you're going to realize actually you will never know. So that's what I wanted to end with. Sorry if that's disappointing. I think it's really cool. But there's still a lot to learn actually about what happens, because and I wish Elisa was here to give the talk, but I hope the next speaker will speak about basically the same thing. But our universe that we look out to, by the way, is a finite volume. Eventually we're going to map it in totality. And probably in most people's lifetimes in this room, I think, if we're lucky. I think maybe 20, 30 years, all gravitation-bound structures will be bound. And I think we can learn, there's still a lot to learn, but there's some things we will never learn. Okay. So that's all I wanted to thank you for your time.
Any questions for Subodh?
How long did it take for you to feel it was okay by you? Because as someone who works in a department, not having the answer is really annoying. And so I don't know, maybe where you alluded to having like different culture upbringing and having that sort of different vision of this particular concept maybe influences how quickly you could come to that conclusion of being okay with it. But yeah, I just wondered if it was.
Yeah, I mean, I think it's like that expression "don't cry over spilled milk." Once you really realize what you're up against, and by the some of my research was actually asking, is there any evidence of this graininess in space-time in cosmological observables? And I was like, probably we'll never know, right?
Yeah.
And, we need these spectacularly accurate, but if you keep asking the question, no, I think I learned something. I think I learned that that this is actually I don't think I have the mental capacity actually to ever. I don't think human beings do Sorry, I know this is not a. I think one of the things that really I wish I could grab all my fellow theoretical physicists and just like keep them in a boot camp and be like it is completely okay to say I don't know. Stop filling the vacuum of the unknown with speculative stuff, right? And this is kind of the industry we live in now. But I think the idea of us not knowing what geometry is at the Planck scale, this is completely well accepted. What are we going to do with that, right? And so I'm actually excited by that. Yeah, I just don't think we as material agents in this emergent thing can actually ask the question, where did the thing come from? We need to be a structure outside of it somehow. Maybe like a Gödel incompleteness type thing.
So what are you researching right now?
Ooh, right now, yeah. So, well, I'll tell you one thing. So the question of the ripples in space-time itself, gravitational waves, did they actually cause the expansion of the universe to change? Do they weigh anything? That's what I'm working on right now, and I think the answer is people have done that calculation wrong. So I have an answer that I show a bunch of colleagues like, yeah, of course, and I show a bunch of other colleagues like, what? That's crazy, and so but it all makes sense, and so that's what I'm working on right now. Yeah.
Thank you for your talk. I heard during the talk I heard a lot about linguistics, and I also believe that the language that you have will influence greatly how much you will understand. Yeah, what is your vision on that? Because you've been in Asia, you have culture and languages from there and from here.
To some extent, right, with actual language like words. I think mathematics is its own language. It's a bit more universal. But you can only describe what you can describe. But what you can, so my answer is, in terms of that, 100% you're limited by the language you have. So I would say this theory that we call string theory, I haven't told you what it is. It's basically the idea that all subatomic particles are vibrations on this thing called a fundamental string. So it has different notes, and all different particles have different notes, and space-time itself is a fluctuation, is one of these fluctuating things. We don't have the mathematics to describe this thing. We literally, we fail. So we try our best, and then we come up with all sorts of crazy things, and we think that maybe we understood something. We don't have the mathematics, so until then I can't even answer the question. So so mathematics is the language of how we describe physical processes, and we are completely bound and limited by that. I will tell you something. So Einstein's theory is a theory of how geometry responds to matter. But it doesn't tell you how topology can change, right? So like, what is topology? It's like if you have a donut versus a sphere, one of these things has a hole in it, the other one doesn't. Can one go from one to the other? We don't have a theory that can describe that process for geometry. We don't know. So I think until we do, we're not allowed to ask these questions. I know that my colleagues would disagree with me, but I think if they thought about it long enough, they would end up being like, yeah, maybe this has something to do with it. So yeah, of course language does bias our perceptions and our views of reality, but I think most people are reflective enough and creative enough to transcend that. I think a lot of us do that in our daily lives. But unfortunately, when it comes to using mathematics, we are literally limited by the tool that we have.
Yeah, could you emphasize again one more time why the uncertainty of the quantum fluctuation, how that connects to answering the question why the question of beginning of time is meaningless?
Oh yeah, okay. So so the idea that nothing can be still, right? So there's always, if you go to smaller scales, something has to be moving. One of the predictions of Einstein's theory, and actually there are many arguments to this, but one of the predictions is if you have enough energy in a small enough region, it becomes a black hole. So a black hole is something that is outside. You can't get inside of it, you can't look outside of it. And then another thing that we've learned is that black holes are actually very small, but they evaporate right away. It's this thing called Hawking evaporation. And so the idea is that if you try to localize a point, if you try to actually say something is here, and that distance is 10 to the minus 35 meters, right? It's called Planck length. You have created enough uncertainty in the speed of something or the energy of something that it creates its own black hole. So at that scale, you have something that becomes a black hole and then it evaporates. So space-time at that scale is fractal. Okay. As a consequence of the uncertainty relation. It's just the same way that you try to zoom in on anything that looks like a continuum, eventually it doesn't. You see substructure. The same thing is true for space-time. What it is, we don't know. There are multiple arguments that indicates there is no such thing as a continuum.
But why do we need the continuum for this question?
Because I would love to write down something on, I don't even know how to write down equations. on something that, so in all my equations I write down something as a function of x. What is x? It's a continuum, right? So we don't have the mathematical structures, the tools to even write down what could resemble laws of physics on this, whatever this is. I don't know what it is. Yeah, I mean, if it were straightforward, there are ideas, by the way, right? There's this thing called matrix models, right? Where like, you know, geometry itself is emergent from these things. We have some calculation, but it's just a guess. We don't know if it's true. There are ideas. Yeah, I think I mentioned what some of the stuff I did in my graduate student days and my early postdoc days was to ask that question. If, you know, let's just model whatever that grainness is in some way. How could we tell what we see? Fortunately, we don't have observations accurate enough to be able to tell the different possibilities apart. But in general, the question of what is geometry, what is space-time at the very microscopic scales is still a debated question. It's still a mystery. I have no idea.
Final question?
Thank you. Could you please tell us what you mean by energy?
Yeah, so energy is, I think we have an intuitive notion of what it is, right? So it's just, you know, if something is moving fast, it has more energy, right? Or if something is, you know, at rest, it has less energy. In cosmology, energy, if you like, is just, according to Einstein's equation, it's just something that likes to curve space-time. That's the definition, that's the thing that makes it do what it does in cosmology in an interesting way. But energy, you know, it actually does correspond to what you intuitively understand energy to be. And so the definition of energy in physics and the definition of energy you have are not that far apart. It's that you know, it takes work to give something more energy, and so, you know, so that's how we loosely can wrap our heads around it. So if something's moving fast, it has to have more energy than something that's at rest relative to you. You have to push it. You have to make it go. So that's one way to wrap your head around. If that makes sense.
Well, it's a bit short in my... I'm looking to find experts like you who have some concept of what it is.
We have a very precise mathematical definition of what it is, right? But it's not something that I think it would satisfy someone saying, but okay, it is this quantity that if your background doesn't change in time, there exists this quantity that is neither created nor destroyed. I'm going to call it energy, right? Everything in nature that somehow isn't created or destroyed, like charge, energy, momentum, are numbers that just are. They're neither created nor destroyed, and they follow from symmetry. So that's the real, if you like, the real definition. But that's a mathematical definition. I'm trying my hardest to make it in a way that, you know, is intuitive, which is where I thought the question was asking. But your notion, your intuitive notion of what energy is, and the physical definition of what energy is are not that far apart. They're actually basically the same thing at the scale that we're at here.
Okay, I think this may allow for some more discussion during the break. Okay, so let's thank Subodh again for his very interesting talk. And then we'll now have a short break for you to allow to get a drink and to ask yourself, well, what makes sense? And then we'll continue in 10 to 15 minutes.